Let's use this kinematic equation to solve this problem 1. So in this problem, we have the velocity given by t squared plus 2t, and we are going to find the acceleration as well as the position when the time is equal to 4. In this case, the particle is moving in a straight line, which is the rectilinear motion. The initial condition is given at t equal to 0, the position is 0. We can easily find the acceleration from the equation 2, where acceleration can be found by differentiate velocity with respect to time. Substitute your velocity inside, differentiate t squared, you obtain 2t, differentiate 2t, you obtain 2. So at t equal to 4 seconds, you substitute inside this, you obtain the acceleration to be 10. The position can be found from the equation 1, where after rearrange the equation, you obtain v dt equal to dx. Integrate both sides and substitute the limit. At the lower limit, you have t0, which is the initial time. t1 is the final time, where you write it in the upper limit. s0 is the initial position, s1 is the final position. From the initial condition here, we can substitute t0 to be 0, x0 to be 0 as well. And at t equal to 4 here, then you have the time is 4 where the position is unknown. Therefore, we let the t1 equal to 4 and s1 remain. So after you substitute velocity inside this equation, you should obtain this. If you integrate t squared, you obtain t power of 3 divided by 3. Integrate 2t, you obtain 2t squared divided by 2. And then don't forget to substitute the limit 0 and 4 here. And on the right hand side, integrate 1 dx, you obtain x. So if you substitute the limit inside and calculate, you should obtain this. And on the right hand side, you should obtain x1. So if you compute, you should have the x1 equal to 37.3. So this is the position at t equal to 4 here. Besides using finite number here to find the position x, it's highly recommend you to use variable t and also variable x here. If you do this, let's say we change this to t, this will be t, and if you substitute t inside, here will become t. So you obtain t power of 3 divided by 3, which is this term, t squared, which is this. On your right hand side, we replace x1 to be x, which is a variable, s1 is a finite number. So this one to be x, substitute x inside, you obtain x only. So this is very powerful because from this equation is valid for all the t. So by substitute t equal to 4, you obtain the displacement at t equal to 4, which is 37.3. Both approaches give you the same answer, but this approach is better because you can obtain the displacement function in terms of time. In this problem 2, you have a particle moving in a straight line, which is the rectilinear motion. Acceleration is given by a equal to square root x, and x is the position in meter. The initial condition is given here at t equal to 0, the position and the velocity are 0. We have to find out the velocity v as well as the time when x equal to 16. Since the given acceleration is in the function of x, therefore we can use the third equation here because we have the acceleration linked with x here. Integrate both sides and put the corresponding limit. So if you have dv, so the limit must be changing from v0 to variable v, and for the ds, you have the limit from x0 to variable s. Since we know the initial condition for the s and v is 0, therefore you can substitute inside. And also we substitute the a equal to square root x into the formula here. Square root x is also same with the x power of 102. Then you integrate both sides. So v here you obtain v squared over 2 and limit 0 to v. And for the x power of 102, integrate, you have 102 plus 1, which is 3 over 2 here. And then you have to divide 3 over 2. So this can be simplified to be 2 over 3. So you substitute v inside, minus with 0 inside, then you obtain v squared over 2 on your left hand side. On your right hand side, substitute x and substitute 0 inside, you still obtain 2 over 3 multiplied with x power of 3 over 2. So 2 here can move to become 4. Then take the square root, which is multiplied with power of 1 over 2. Same on both sides. Then this term can be cancelled, you obtain v. So 4 over 3 square root, you obtain 2 over square root 3. And then here you have 3 over 4. With that, you success to find the velocity function. What you need to do next is substitute the x equal to 16 inside. Then you get the answer for the velocity at x equal to 16. We have success to obtain the velocity function previously. So once you substitute x equal to 16 inside this formula, you should be able to obtain v equal to 9.24. So this is the answer for the velocity. To find the time at x equal to 16, you can substitute the velocity inside equation 1. Once you substitute velocity to be this, then you get this equation. Move the dt to the left hand side, so you can cancel this to have this. And then move the x to the right hand side, so positive 3 over 4 becomes negative 3 over 4. Then we can integrate both sides. So based on the initial condition here, you start from 0 to variable t. Based on the initial condition for x, you start from 0 to variable x. Then you obtain this equation. Integrate the constant, you obtain the constant multiplied with t. Integrate the x to the power of negative 3 over 4. Then you have positive 1 at top, which is 1 over 4 here. And you need to divide it by 1 over 4. So therefore you obtain 4 here. After you substitute the limit 0t inside, you still obtain this answer. On your right hand side, after you substitute the limit 0 to x, you still obtain the same answer here. Then you rearrange the t to be on your left hand side, and you should get this. And substitute the x equal to 16 inside, you find the time equal to 6.93. So this is the time required to move from x equal to 0 to x equal to 16. And in this problem, you success to learn how to determine the velocity with respect to the displacement, as well as to find the time with respect to the displacement. You can also find the velocity in the time function by using the first equation, and also you can find the acceleration with respect to time function by using the second equation. If you express your x on your left hand side equal to the function of t, then take the differentiation dx over dt, you should obtain the velocity, and differentiate again d square x over dt square, then this is the acceleration. In this problem, we are going to investigate the rectilinear motion with constant acceleration. So we let constant acceleration to be ac. We want to simplify these three equations when we consider the acceleration is constant. For example, in the equation 2, we have the acceleration equal to differentiation of velocity with respect to time. So dt can move to the left hand side to become a dt, and after you integrate both sides and put the limit, you should obtain this equation. If we assume the acceleration is constant for t greater than 0, then since the acceleration is constant, we can take it out from the integration, and we let the initial time to be 0. Integrate dt, you obtain t. Integrate dv, you obtain v. And if you substitute the limit v and v0 inside, you obtain v minus v0. Move the v0 to the left hand side, then you obtain your v equal to v0 plus act. So this is equation A. From equation 1, you have the v equal to dx over dt here. And from equation A, you have v equal to v0 plus act here. So with that, we focus on this component. Let's take dt to the right hand side. You should obtain dx equal to v0 plus act dt. Integrate both sides and substitute the limit. Then we can perform the integration. On the left hand side, you have x, and after you substitute the limit, inside you obtain x minus x0. On the right hand side, integrate v0 dt, you obtain v0t. Integrate act, you obtain act squared divided by 2. So you need to substitute the limit t0, and don't forget the summation. After you perform the integration, you should obtain this, and move the x0 to the right hand side, you should obtain equation b. Let's continue with the equation 3 here. Integrate both sides and substitute the limit, then you should obtain this equation. Since AC is constant, we can take it out. Integrate v with respect to dv, then you have the v squared over 2. After you substitute the limit inside, then you should get this answer. On the right hand side, integrate dx, you obtain x, and if you substitute the limit inside, x0 and x, then you should obtain this answer. Remove 1 over 2 by multiplying both sides with 2, and then move v0 squared to the right hand side. You should be able to obtain equation C. So far, we have success to simplify these three equations into equation A, B, C when the acceleration is constant. So this is the vector equation where we consider the magnitude and also the direction. If the direction is known, we can further simplify the vector equation into scalar equation, which is only consider the magnitude. So these are the kinematic equations that you know so far. So in general, we have equation 1, 2, 3. When the acceleration is constant, we can simplify this equation into equation A, B, C. In this problem, a ball was thrown straight up in the air from 1.2 meter above the ground. So let's say this is the ground. So above the ground 1.2 meter, you have a ball. You can imagine the ball move to the maximum position here and then fall back to the ground in 3 seconds. We want to know what is the maximum height it reached, which is here denoted by S. Let this point to be 1, so this is your S1. Let this point to be 2, this is your S2. So at x3, you have 0. So this is the initial position, which is the t1 equal to 0. And then at t2, which is here, we don't know the time taken to reach there. And then for t3, is given 3 seconds. We are using the notation moving upward to be positive and moving downward to be negative. So your initial velocity at point 1 here must be positive to move up, but the value is unknown. When you reach to the maximum position here, the velocity here should be equal to 0 because it doesn't move further. Then it starts fall back and the velocity keep increasing in negative direction. So at position 3 here, your velocity 3 is equal to negative, but the value is unknown. How about the acceleration in point 1, point 2, and point 3 here? The force that is acting on the object all the time is the F equal to mg, which is due to the gravity. Therefore, the particle is experiencing negative 9.81 for the acceleration. Since the gravity is pulling the object in this direction, therefore you have negative. So these are the information that we obtained so far. Let this point to be 0, let this point to be 1 for the maximum position. At the ground, you have position 2. So you start at x0 equal to 1.2 meter and you are going to find the x1, which is the maximum height. And we know that the acceleration is negative 9.81 experienced by the ball at all positions. From the equation B, so for AC we know it to be negative 9.81. So for the x0, it starts from 1.2. V0 we don't know, so this one unknown. And then T is the time taken. So let's say for the T is from 0 to 3. The time taken to point 2 will be equal to 3. So we can substitute 3 inside the T here. So S here is the displacement at point 2. So which is equal to 0. Substitute 0. X0 is 1.2. AC is negative 9.81, and then T is 3 here also. Calculate this equation, then you should obtain the V0 to be 14.3. By using equation C, substitute the V0 to be 14.3, AC to be negative 9.81, X0 to be 1.2. So you have the V and X. Substitute the V1 inside, then you should be able to obtain X1 to be 11.6. You might think that we can substitute the X2 equal to 0 inside here, and then V2, which is unknown. So once you solve this, you can find your V2. If you compute the right hand side, you should obtain 228, and then if you take the square root, you obtain 15.1. This value is the magnitude of velocity at point 2. We do not know the direction for velocity at point 2 here yet. Let's continue to use the equation A to solve the problem. Substitute V0 to be 14.3, AC to be negative 9.81. Let's say time taken to T1 is unknown and the velocity at point 1 is 0. So after you substitute, you should obtain the T. You should get the T1 equal to 1.46. By using similar step, substitute T2 inside here, and then V2 is unknown. So you can solve this. You should get V2 equal to negative 15.13. We success to find all the kinematic parameters by using these three equations. We are going to discuss the example that involve continuous and erratic motion. If you have the motion or displacement that can be defined by one equation, when you plot the graph, there is no discontinuity. So this is a continuous motion. By follow equation 1, take the differentiation on the displacement with respect to time, then you obtain the velocity. So in this case, differentiate 15t, you obtain 15. Differentiate 150, you obtain 0. So you obtain 15 for your velocity. If you take a differentiation again, it's called double differentiation. So differentiate the velocity, then you obtain 0. So you can see the result in your plot is 0. On the other hand, if you have the acceleration, you can obtain the velocity by performing the integration. You have additional term for the constant, and this can be found by using the initial condition. For example, velocity is equal to integration of acceleration with respect to time. So since your acceleration is 0, then the answer is constant. So this velocity means at any time it will be equal to constant. If the initial condition is given, for example at this point, your V0 is equal to 15. By substitute the initial velocity inside this formula at t equal to 0, then your V will be equal to c. And V0 will be equal to 15. So we obtain the c to be 15 and your Vt is equal to 15 after you substitute the c. So we obtain the constant 15 for the velocity. You can find the displacement by integrate the velocity with respect to time. So you integrate 15 dt, then you obtain 15t plus constant for your displacement at any time. And you can find the constant 2 here by using the initial displacement. So your x at time equal to 0 will be equal to negative 150. Substitute this inside the equation, you obtain x0, which is equal to 15 0 plus your c2, and this is equal to negative 150. Therefore, this term can be cancelled and you obtain the c2 equal to negative 150. So we can replace the c2 by negative 150, and this is your answer for the displacement. And when you plot this, you should obtain the answer here. For the erratic motion, the motion is expressed in many functions, and in this form we say it's a piecewise function. You can see the equation is equal to 0.4t for the first time interval from 0 to 10 seconds, and acceleration is equal to 2.4, which is the constant at second time interval 10 to 20 seconds. Lastly, acceleration is 0 at 20 to 30 seconds. So when you plot the graph for the time interval 0 to 10 seconds, then we use the formula 0.4t to plot it. Then you continue for the second interval within 10 to 20 seconds by using the second equation here, which is a constant. Lastly, you have 0 from 20 to 30 seconds. So you see the motion is discontinuous at these 2 points as well as here. So this is called erratic motion. Then you integrate acceleration to obtain the velocity. For dt, the limit changes from t0 to variable t. For dv, the limit changes from v0 to variable v. Since the initial condition is given here at t equal to 0, the displacement and velocity it will be 0. Then we can substitute t0 to be 0 and v0 to be 0 here. Let's start with the first time interval here, and you substitute the acceleration 0.4t here. When you integrate, you obtain 0.4 t squared divided by 2. And don't forget the limit t and 0. So once you substitute the limit t and minus with 0 inside, you obtain 0.2t squared. On the right hand side, if you integrate, you obtain v, and therefore you obtain this answer. At the end of the time interval, which is 10 seconds, so you need to find the velocity at 10 seconds, which is equal to 20. For the second time interval, the acceleration is 2.4, but the initial time and also the initial velocity is no longer the same. So you need to change it to 10, and then velocity at 10 seconds you obtained previously here, it will be equal to 20. Therefore, you can proceed with this integration. Integrate 2.4, you obtain 2.4t, and then the limit, you substitute t 10 inside, then you obtain 2.4t minus with 24. On the right hand side, you obtain v, and the limit v20, so you obtain v minus 20. So 2.4t minus 24 equal to v minus 20. Move 20 to the left hand side, then you obtain negative 4 here. So the velocity is equal to 2.4t minus 4. And when you substitute the 20 seconds inside this formula, you obtain v20 equal to 44. Then you can continue with the last equation where you have the acceleration equal to 0. The initial time is changed to 20 now, so you have to find the velocity at 20. So you substitute 44 inside v0 here, then you can proceed with this integration. Integrate 0t, give you 0t, and then don't forget the limit t and 20. So if you substitute the limit, you still obtain 0. On the right hand side, you obtain v minus 44. So 0 equal to v minus 44, therefore v will be equal to 44 here. If you substitute 30 seconds inside this formula, you obtain v at 30 seconds to be 44. So this is the velocity function that you obtained previously in the piecewise format. By integrate the velocity with respect to time, then you can obtain the displacement. So the velocity is equal to 0.2t squared from 0 to 10 seconds, which is over here. And then the velocity is equal to this from 10 to 20 seconds, which is here. Lastly, you have the velocity equal to 44 from 20 to 30 seconds. First of all, substitute the velocity to be 0.2t squared here and use the initial time to be 0. Previously, the initial displacement is given by 0, therefore we can substitute 0 for the x0. After integrate, you should get the answer for this, and then if you substitute the 10 seconds inside this function, you should obtain the x equal to 66.7. Repeat the same procedure for the second time interval here. Substitute the velocity inside, and the initial time now changed to 10. The initial displacement now at 10 seconds will be 66.7. Then you should obtain this answer, and if you substitute 20 seconds inside, you can find the displacement at this time. Next, we continue with the third time interval here. So velocity equal to 44, substitute inside, and the initial time is 20. At 20 seconds, the displacement is 387 here. Then solve the integration, you obtain this answer. At 30 seconds, you have the displacement equal to 827. Then you can obtain the displacement in the piecewise function, and if you plot this, you should obtain this graph. In this problem, it shows that for the erratic motion, you need to perform the integration part by part. So you have to continue from the first interval and then continue with the second time interval and so on. Different with the continuous motion, the erratic motion applies the kinetic equation to each separate motion. In many cases, not only acceleration versus time, acceleration versus displacement graph is also important, as well as the velocity versus displacement graph. You can express the t in the function of x here, and then substitute the variable t inside the acceleration and also the velocity. By doing that, you can convert the acceleration with time function into acceleration with x function. Same to the velocity, you can obtain vt to vs. Please check this answer and see if you get a correct ax as well as the vf.